Hello everyone, I am Vaishnavi from the Department of Chemical Engineering. I am working as an assistant professor in Erode Sengunthar Engineering College. Okay, uh, now this is a video for GATE preparing students, which is very easy and for just we want to discuss about some problems regarding the heat and mass transfers. Okay, right. I hope the presentation is visible. This is regarding the AICT PRERANA for preparing for higher education for SC students through GATE. Okay. Now we are going to discuss some problems regarding the heat and mass transfers. Okay. A wall furnace is made up of inside layer of silica brick 120 mm thick covered with a layer of magnesit brick 240 mm thickness. The temperatures at the inside surface of the silica brick wall and outside the surface of the magnesit brick wall are 725 degrees Celsius and 110 degrees Celsius. The contact thermal resistance between the two walls at the interface is 0.0035 degrees Celsius per watt per unit wall area. If thermal conductivities of silica and magnesit bricks are 1.7 watt per meter degree Celsius and 5.8 watt per meter degree Celsius, now you have to calculate the rate of heat loss per unit area of walls. Okay. Uh, the given data, L1 is given and K1 is given as L1 is given as 120 into 10 to the power minus 3 meter. K1 is given as 1.7 watt per meter degree Celsius and the L2 is given as 240 into 10 to the power minus 3 meter. K2 is given as 5.8 watt per meter degree Celsius and T1 is given as 725 degrees Celsius and T4 is given as 110 degrees Celsius. And then earth contact is given as 0.0035 degrees Celsius per watt and area can be assumed as 1 meter square. Okay. Then we have to find out the value for Q. We know the formula for finding out the Q is delta T overall divided by summation of RTH, that is equal to delta T overall can be written as T1 minus T4 and the summation of R value can be written as R1 plus RTH contact plus RTH2. Okay, we know only the value for T1, T4 and RTH constant, not a constant, it is a contact. Okay, here T1 minus T4 is given as T1 we know the value and T4 we know the value, so subtract and you will get the answer as 6.615 degrees Celsius. Then RTH value is given as L1 divided by K1A. This is the formula for finding out the R value. So substitute, we know all the values and so we have to substitute the value for L1, K1 and A and you will get the answer as 0.0706 degrees Celsius per watt. The same can be the same will be calculated for R2, L2 divided by K2A, 240 into 10 to the power minus 3 divided by 5.8 into 1. 1 is area. Okay. Okay. Now you know all the values. Um, so substitute in the main equation and you will get the answer for Q as 5324.67 watt per meter square. This will be the answer finding out by substituting all the values for Q. problem. This is the given data. And this is the formula for finding out the Q value. So Q is equal to delta T overall divided by summation of R value. This is the common formula for finding out the Q value. Okay. Then this is okay. Now the second problem: a furnace walls made up of three layers, one of fire brick, one of insulating brick, and one of red brick. The inner and outer surfaces are at 870 degrees Celsius and 40 degrees Celsius respectively. They have given the respective coefficient of thermal conductivities for all the three layers 1.0, 0.12, and 0.75 watt per meter Kelvin, and thickness have been given as 22 centimeter, 7.5, and 11 centimeter. Assuming you just assume that all the layers are in a close bonding of the layers at their interfaces. Okay, now the same thing we have to find out is the rate of heat loss per square meter per hour and the interface temperatures. Okay, they have this is the given data. This for a composite wall without convention. They have given L1, K1, L1 is given as 22 into 10 to the power minus 2 meter, and K1 is given as 1 watt per meter Kelvin, and L2 is given as 7.5 into 10 to the power minus 2 meter, K2 is given as 0.12 watt per meter Kelvin, L3 is given as 11 into 10 to the power minus 2 meter, and K3 is given as 0.75 watt per meter Kelvin. And then they have mentioned two temperatures, inner and outer surface temperatures, 870 degrees Celsius and 40 degrees Celsius. From this, we have to find out the value for Q. We already know the formula for finding out the Q. The same formula has to be used here also. So Q is equal to delta T overall divided by summation of RTH. So delta T overall has to be simplified as T1 minus T4. So you know the value for T1 and you know the value for T4. Substitute that and you will get the answer for delta T overall. So 830 degrees Celsius. And then summation of Rth value, you will get the RTH1 plus RTH2 plus RTH3, and assume area as 1 meter square. So RTH1 is you have the simplification of the formula for RTH1 is L1 divided by K1 into A. Okay, so you know the value for L1, you know the value for K1, and you know the value for A. So substitute all the values for finding out the RTH1, and you will get the answer as 22 into 10 to the power minus 2 kilo uh, Kelvin per watt. Okay, so the same to be continued for RTH2 and RTH3, and you will get the values for RTH2 as 0.625 and RTH3 for 0.1467. So you know all the values, and now you have to substitute all the values in the main equation for finding out the value for Q. By substituting all the values in the main equation, Q is equal to T1 minus T4 divided by RTH1 plus RTH2 plus RTH3. You will get the answer as 836.95 watt per meter square, and you have to convert it to joule per hour. So the conversion will be available in the calci. So you will get the answer after conversion is 3.01 into 10 to the power 5 joule power joule per hour. Okay, just go through it. Okay, we can go for the next problem. The two large parallel planes with emissivities, two parallel planes are given with emissivities of zero point 0.3 and zero point 0.5 and are maintained at a temperatures of 527 degrees Celsius and 127 degrees Celsius. A radiation shield having emissivities of 0.05 on both sides is placed between them. Okay, then you have to calculate the heat transfer rate between them without shield and heat transfer rate between them with the shield. Okay, so given data are emissivities 1 is 0.3 and the emissivity 2 is 0.5 and the radiation shield having the emissivity is epsilon is equal to 0.05. So the two types of temperatures has been given in the Celsius. So we have to calculate it for Kelvin. So 527 plus 273 is equal to 800. 127 plus 273 is equal to 400 Kelvin. Okay, this is the given data for finding out the mm, heat transfer rate. This is the diagram for radiation of heat exchanges. Shield is placed in between the two parallel plates. Now we have to calculate the Q value without shield. First of all, we have to find out the value for without shield. So summation of sigma into T1 power 4 minus T2 power 4 divided by 1 divided by sigma 1 plus 1 divided by sigma 2 is minus 1. This is the formula. We know the value for yes, the sigma for the shield is taken as a constant as 5.67, and maybe that yes, and then you know the value for temperature T1 and T2. 800 divided by 100 the whole power 4 minus 400 divided by 100 the whole power 4 divided by 1 divided by epsilon 1 is 0.3 and 1 divided by epsilon 1 is epsilon 2 is 0.5 minus 1. So for finding out the net without shield is 5024.5 watt per meter square. The same has to be the same formula. But there is a slight change for with the shield. So sigma into T1 power 4 minus T2 power 4 divided by 1 divided by epsilon 1 plus epsilon 3. That means epsilon 3 is nothing but epsilon. Okay, minus 1 plus 1 divided by epsilon 3 plus epsilon 2 minus 1. Okay, so now we have to substitute all the values. Um, Okay, now we know the value for T1 and T2, and we know all the values of epsilon, and now calculate the value for Q with the shield is 859.45 watt per meter square. Okay. Uh, Okay, this is that's all. We have find out the value for heat transfer with shield and without shield. This is the problem, and just one glance. Okay, we can go for the next problem. Emissivities of two large parallel plates maintained at 800 degrees Celsius and 300 degrees Celsius are 30.3 and zero point 0.5 respectively. Find the net radiant heat exchange per square meter of the plates if a polished aluminum sheet epsilon is placed between them, that is epsilon is equal to 0.05. Then find the percentage of reduction in heat transfer. The same thing what we have discussed in the last problem. Here the one small difference is they have asked to find out the percentage of reduction in heat transfer. So they what in the given data what they have given is T1 is equal to 800 degrees Celsius plus 273, that means 1073 Kelvin, and T2 is equal to 300 degrees Celsius plus 273, that is equal to 573 Kelvin. So epsilon 1 is 0.3 and epsilon 2 is 0.5. Then epsilon is 0.05. Okay, radium shield emissivity. Okay, this is the diagram which represents the question. A small a polished aluminum shield is placed in between the two parallel planes. Okay. Now we have to find out the net radiant heat exchange per square meter, and Percentage of reduction in heat transfer due to radiation shield. Okay, the first case, heat transfer without radiation shield, it can be heat exchange between two large parallel plates without radiation shielding it. Shield is given by Q is equal to epsilon into sigma into A T1 power 4 minus T2 power 4. So epsilon bar is equal to 1 divided by 1 divided by epsilon 1 plus 1 divided by epsilon 2 minus 1. It is equal to, now substitute all the values, we know all the values and substitute it, and you have to find out the value, you will get the value for epsilon. Okay, now the second thing, heat transfer without radiation shield has to be found out. So without also for the same procedure, and you will get the value as 15.8 into 10 to the power minus 3 watt per meter square. Okay. The second is heat transfer with radiation shield. For finding out the MEC heat transfer in with the radiation beam or shield, whatever the heat exchange between plate one and a radiation shield 3 is given by, you will have the formula for Q13 is equal to epsilon. Q13 is epsilon bar sigma into area into T1 power 4 minus T3 power 4. Okay, substitute. Now you have to first find out the epsilon bar, and you have to substitute all the values, and then the heat exchanged between radiation shield. Um, okay, now heat exchanger. Um, we have find out the value for heat exchange with radiation shield, and okay, with the radiation shield. Now Q13 is equal to Q3Z. So you have to equate these two equations. Uh, Okay, now we have to substitute all the values for Q13 and Q32, and you have to equate it and find the value for T3 shield temperature. By simplifying all the equations, you have to find out the value for T3. Okay, now you have to substitute all the values. Once it has been substituted, you will get the value for T3. So that is named as shield temperature for T3 is equal to 913.8 Kelvin. Okay, now with radiation shield also you are having the same formula and substitute all the values in the same formula. Uh, Now you have to calculate the percentage. Once you have calculated the Q13 formula, the percentage of reduction in heat transfer due to radiation shield can be given as Q without shield and Q with shield. Now you know all the values and substitute in the above equation, and okay. This is the procedure for finding out the percentage reduction of the reduction in heat transfer due to radiation shield. Okay. Okay, that's all. This is this problem is that's all. We just go through it. Okay. Now we can see the next problem. Two rectangular surfaces are perpendicular to each other with a common edge of 2 meter. The horizontal plane is 2 meter long and the vertical plane is 3 meter long. The vertical plane is at 1200 Kelvin and has an emissivity of zero point 0.4. The horizontal plane is 18 degrees Celsius and has a emissivity of zero point 0.3. Now you have to determine the net heat exchange between the plates. Okay. Okay. Now this is now you have to find out the value for Q. Here you have to substitute the value for Q in the equation of Fg 1 to 2 and A1 into sigma T1 power 4 minus T2 power 4. So for finding out the Fg1 to 2, you have the equation here as 1 divided by 1 minus sigma 1 divided by sigma 1 plus 1 divided by F1 to 2 plus 1 minus sigma 2 divided by sigma 2 and A1 divided by A2. Okay, here what they have given is A1 is equal to area of horizontal planes, that is equal to xy, that is equal to 2 into 2, 4 meter square. The same as for A2, area of vertical plane, that is equal to zx, that is equal to 3 into 2, that is equal to 6 meter square. Then both for both the surfaces, we have a common edge for which z divided by x is equal to 3 by 2, that is equal to 1.5, and y divided by x is equal to 2 by 2, that is equal to 1. So from the data book, heat and mass transfer data book, the shape factor for F1 to 2 is noted as 0.22. So substitute all the values and you have to find out the, now you know the value for first you calculate the value for Fg1 minus 2 by substituting the F1 to 2 value from the heat and mass transfer data book, and once it has been substituted all other values are known, so substitute all other values and get the value for Fg1 to 2, so you will get the answer as 4, I think so, yes. So 4 into A1 into sigma summation of T1 power 4 minus T2 power 4. This is the um, yes, after substituting all the values in the qth equation, then you will get the answer for, once all the values have been substituted and simplified, you will get the answer for q as 61657.7 watt. Okay, that's all. Just have a glance. Next problem, the filament of a 75-watt light bulb may be considered as a black body radiating into a black enclosure at 70 degrees Celsius. The filament diameter is given as 0.10 millimeter and length is 5 centimeter. Considering the radiation, determine the filament temperature. Here, consider that one light bulb has to be varied with the temperature. Okay, the filament inside the light bulb is of 75 watt, and it is to be radiating into a black enclosure at 70 degrees Celsius. The filament diameter is 0.10 mm and the length is 5 centimeter. So now considering the radiation, you have to determine the filament temperature. So what is the given data? Q is equal to 75 watt is equal to 75 joule per second. Then T2 is equal to 70 plus 273, that is equal to 343 Kelvin, and diameter d is equal to 0.1 mm, and length is equal to 5 centimeter, and area is equal to pi into dl. So now we have to um, s- get into the solution. Emissivity is equal to 1 for black body. So Q is equal to summation of sigma into epsilon into A into T1 power 4 minus T2 power 4. Therefore 75 is equal to 5.67. So Q is equal to 75 they have given. So here what you have to find out means the temperature. Okay, T1. One temperature is given, so you have to find out the another temperature. So Q 75 is equal to 5.67. Yes, sigma value is a constant value. 5.67 into 10 to the power 8 minus 8 into summation is given as 1 into pi into diameter has been given, and length has been given. 0.1 is a diameter and 5 is a length. So after substituting all this, you have to T1 power 4 minus T2 power 4. So T1 is you have to find out the value for temperature, uh, filament temperature, and another temperature has been given as 343 Kelvin. So now substitute the values for finding out the T1 power 4 is 75 divided by uh, so now you have to calculate the T1 power 4. Okay, 75 divided by 8.906. This is a gas constant into 10 to the power minus 13 plus 343 the whole power 4. Now you got the value for T1, and then okay, so this is the value for T1 is the filament temperature. Okay, the next problem. The sun emits maximum radiation at lambda is equal to 0.52 mu. Assuming the sun to be a black body, calculate the surface temperature of the sun. Also calculate the monochromatic emissive power of the sun's surface. So what is given is lambda max is equal to 0.52 mu, that is equal to 0.52 into 10 to the power minus 6 meter. So you have to find out the surface temperature, monochromatic emissive power, total emissive power, and maximum emissive power. So T monochromatic emissive power is E is equal to by B lambda. Then total emissive power is given as E, and maximum emissive power is given as E max. Okay. From Wayne's law, the lambda max into T is equal to 2.9 into 10 to the power minus 3 meter Kelvin. This has been taken from the heat and mass transfer data book. Okay, so we have to substitute all the values. So T is equal to 2.9 into 10 to the power minus 3 divided by 0.52 into 10 to the power minus 6. So you will get the answer as T is equal to 5576 Kelvin. The second problem, what is the monochromatic emissivity power? Okay. Then for finding out the monochromatic emissive power EB lambda from Planck's law, EB lambda is equal to C1 into lambda power minus 5 divided by E power C2 divided by lambda T minus 1. From this heated mass transfer data book, in the sixth edition, you will get the values for C1, C2, lambda, and T. So substitute all the values and you you just check overall. So next, now you have to substitute all the values in the um, this EB lambda value in monochromatic emissive power formula, and have the answer as 6.9 into 10 to the power 13 watt per meter square. Then the total emissive power can be found out as E is equal to sigma into T power 4. You know the value for sigma and T power 4, substitute and get the answer. Then the last question, maximum emissive power. Uh, The last thing, the maximum emissive power can be calculated as Emax is equal to 1.285 to 10 to the power minus 5 T power 5. So substitute the value for T power 5 and you will get the answer for maximum Emax in watt per meter square. Okay, that's all. Just have an idea. That's all today's PPT. I hope everyone have understood the problems and be very clear in the basics. Whatever the subject you have taken for preparing for gate exams, whatever the subject may be, you have to be in a clear cut with the basics and um, time management is very important for solving the gate problems. So keep in mind about the timing and you have to calculate the timing and for formula and all you just calculate it uh, very roughly. You should know the formula very clearly. For that you have to be very clear with your basics. Then Then what else for GATE? Uh, Not only heat transfer, mass transfer, very very important subjects related to chemical engineering are heat transfer, mass transfer, thermodynamics, transport phenomena, fluid mechanics, see, chemical process calculations, and CPI, chemical process industries. These are all main core chemical reaction engineering. These are all the main important core papers related for GATE. You have to be clear with the basics of these subjects, then you can make through it and clear it. um, just prepare well. All the very best. Thank you.